Any questions?
No.
How you doing, Aaron?
Good.
Good. Ryan, any questions?
No, I'm good.
Okay, then we will go right to this. And talk about these other forces. So the other day we mentioned that the pressure gradient force. A pressure gradient is the change in pressure over a distance. So I'm going to use D. From now on, I'm going to use D. And understand when I do this or this, X would be a horizontal distance, and DZ is a vertical distance. And I'm talking about the change. And because I'm using this notation,
That's a question.
because I'm using that, I'm talking about the instantaneous pressure gradient, or basically what, instead of you, I wouldn't say, like, I would say velocity is instantaneous, but I wouldn't say the pressure gradient force is instantaneous, but I'm saying that is the PG at a point. So that's the, instead of instantaneous, which is over time, this is going to be at a point. So I don't really use the word instantaneous with this thing, okay? And then my pressure gradient force, what makes it a force is if I divide it by rho. And look, what you need to think about this is that rho is mass over volume. So this is in the denominator. What this is, it's going to be volume over mass dP dx, right? That's what it is. And I'm saying that F equals MA. The units is going to be meters per second squared. So this is actually, it's an acceleration, right? The reality is we are looking for things that are accelerations, not forces. But what is a force equal to acceleration? Are they the same thing? And the answer is they're not the same, because force doesn't equal acceleration. Force equals mass times acceleration. But instead of putting it there, what if I put the mass over there? Do you understand that I'm saying that an acceleration is a force divided by mass? But isn't that what I have? Is I have a force divided by mass. So I'm using accelerations to talk about forces, but they're really, an acceleration is a force, and it's what we would say, if you want to know it correctly, it's a force per unit mass. Have you ever heard something like this ever? Per unit mass or per unit quantity or something like that? What this means is you're saying the mass is equal to 1 kilogram. So unit, like the word unity, means 1. So if I put 1 in the denominator, 1 kilogram, do you agree that force equals acceleration?
Mm-hmm.
So this is how we do it. That's not a big deal. I just wanted you to understand that a force causes an acceleration, but in this case, because it's force per unit mass, it is an acceleration. And that's what I'm going to use. So this becomes the PGF, and that's the way we say it. That's the pressure gradient force. Now, we already know about gravity. Gravity is G. You agree that gravity, we said, is a force, but it's actually a force per unit mass because we give it to you in acceleration units. It's a 10 meters per second per second. Now, what about the Coriolis force? The other day, we said the Coriolis force is 2 omega v sine phi. This is Greek letter omega. What does omega stand for? This is in the notes. What does omega stand for? What does it say in my notes? Am I recording? Yeah, okay. What does it say, Leland? Did you find it?
It's the rotational frequency of the Earth.
It's the rotational frequency of the Earth. How far does the Earth rotate? What's the rotational frequency of the Earth, Ryan?
It is 7.
No, don't give me that number. In your own words, what's the rotational frequency of the Earth?
I guess it's how fast the Earth is rotating.
Not how fast, how frequently. We don't say how frequently do you do something. What do you say? Like I don't say. Go ahead. What were you gonna say?
The frequency would be it rotates once every 24 hours.
So once in 24 hours, right? Once a day. The question is, how much is once? How much is once? What does that mean? Zach?
Would it just be like one rotation? Like,
How much is that? I mean, it's not one, right? Once is not a
yeah.
thing. How much is a rotation?
Would it be like the amount of time it would take you if the Earth, like the circumference, I'm guessing, with
Well, yeah, but
latitudes?
you said it's one rotation. Well, we already know the time, right? We said the time is 24. But what is one rotation? How much is one rotation? Lena, what do I mean by that? Now that I know you're going to operate heavy rigs, this is something you should understand.
Oh yeah.
When I'm running an engine,
That
How
would be like
fast?
rotations per minute.
right? RPM. So show me a rotation with your hand. Because how much is that? Aaron, do you know?
Well, she said 360 degrees.
Yeah. So you would say that one rotation, I mean, one way to write that is 360 degrees. Now, a Coriolis force has to be in meters per second, right? This is going to be meters per second, meters per second squared. I already know that the velocity is a meter per second. This no unit, we'll explain this in a second. So this unit has to be what? It has to be per second. But what did I say a per second is? We've done per seconds before. Sam, where have we talked about per seconds?
Like gravity.
No, we've
Well-
talked about per seconds.
Yeah, well, velocity of falling.
No. Way back, further in class, way back. Ryan?
So for frequency of a wavelength, it would be in hertz.
We talk about a wavelength, we call it a hertz, right? That's a frequency. And a frequency was per second. And we said we didn't like the way they used per second, so we call it a hertz. But basically, we're saying that's a frequency. And I'm saying that this is a frequency. However, notice that this is in hours. And what do I need it to be in? This is a
Seconds.
per hour. I need it to be per second. So first thing I need to think about is that I've got to multiply this by 1, because any number times 1 equals itself. Remember? Identity property of multiplication. So how many? There's 60 minutes in 1 hour is equal to 60 minutes, isn't it? And therefore, the hours go away, and I'm left with now I have degrees per minute. But then I know, then what do I multiply it by?
One minute over 60 seconds.
Okay, 60 seconds. And then the minutes cancel, and then I'm left with a second in the denominator, which is a per second. The only thing is, do you know that this is a unit? So this is actually degrees per second. But I don't want a degree, which is a unit. I want the unitless equivalent to degrees. Do you know what I'm talking about? How far is the unitless equivalent of 360 degrees?
That'd be radians.
How many?
2 pi.
So it's going to go 2 pi radians. Then I have what I need. So right now, omega is this. That's what omega is. So take your calculator out and do this problem. Put it in scientific notation and tell me what you get. So you're going to run the calculator to do this. Aaron, are you familiar with radians? Like 2 pi radians is 300 degrees?
Not really.
Okay. Well, so in other words, that's all I'm saying. That's just something you should know. So what do you get for this answer? Is this the number you get? Really? I don't think so.
Yeah, mine was slightly different.
What'd you get, Zach?
I got 7.272 times 10 to the negative 5th.
That's what you should have gotten if you did this. So why is it different? Did you make a mistake? Did I make a mistake? Why is this wrong? Or why, in other words, why did you get this number, which is what you should have? If you did this with your calculator, that's the number you should have gotten. And I'm giving you this number. Why?
Would it be because of like how a day isn't exactly 24 hours?
Is a day shorter or longer?
Slightly longer.
No, the other way. It's a little
Oh,
shorter. 23 hours, 56 minutes, right? That's 23 hours and 56 minutes is how long it takes the Earth to make one rotation. So Zach, what basically saying is that 24 hours means I'm adding that little bit of extra time to get back to noon. So I guess you could say that the day, that 24 hours is slightly longer than it takes to rotate. That's called the sidereal day. Sidereal is spelled, but you don't even know that for this class. But so this number in the denominator is a little bit smaller, which makes omega a little bit larger because this is A equals B over C. You see how this is, how many times have we used A equals B over C this semester? Almost everything, right? That's why it's the most important equation. So the actual answer is this. So this, when you see omega, that is the number you always consider. You multiply by 2. I'm not going to explain why. I teach an intermediate class which will prove what these things are using calculus. It takes several hours to do it. It's very fun. I like it a lot. I know what the velocity is. What the hell is this thing? What is sine phi? So first thing is, this is Greek letter phi, like phi, phi, pho, phum. Phi stands for the latitude. Okay, so what you do is you plug in the latitude. Okay, does that make sense? Okay, then sine of this. That's what I do. I do the sine. Sine, it says sin, but it's actually shortened word for sine, is a function. So what I'm going to do is ask you, what's a function?
Put something in, you get something out.
That's the way I'm going to do it. Now, Zach, you've taken math, right?
Yeah.
Are you still taking math?
Yeah, I'm doing trigonometry this semester.
Okay, so you do trig functions. Sine is a trig function. So do a Google search, define function, and tell me what you get.
A relationship expressing, and a relationship or expression involving one or more variables.
Okay, what else do you see? Anything more exciting? Math books tend to go crazy about this.
I can look at the Wikipedia page. In mathematics, a function is a binary relationship between two sets that associates to each element of the first set exactly one element of the second set.
Yay! Let's make things harder than it needs to be. But that's exactly what it is. It's a binary between two elements of two sets, and the one set is corresponding to, it's like, what kind of nonsense? So what I'm going to say is a function is something that takes a number, it funks around with it, and it gives you a number back. So I'll give you an example. The function is x. Give me a number. Give me a number.
5.
5. I plug in the 5 into x, and you know what I get back out? 5. Oh, that was hard. Here's a function, x plus 1. If I plug in the number 5 into this function, what do I get back out?
6.
6. Wow, that's really hard, isn't it? How about if I do this instead of x plus 1? What if I said the function is 2x? Plug in 5, what do I get?
10.
Okay, every time I plug in 5, I get back 10. Everything I plug in, I can plug in whatever I want and I get something back, but I always know what I'm getting back. That's what makes it a function. Now, numbers I plug in, numbers in, there's a name for that. What do you call the numbers you can put in there?
Variables.
Well, X is a variable. I can plug in anything into it, but there's a name for the ones that you're putting in. It's called the domain. What numbers am I allowed to put in to this function? Okay. What do you get? You get a number back out, right? What is that called? What do you call the numbers you get out of the function?
That'd be range.
That would be range. And see, that's all it really is. The numbers that you're allowed to put in is called the domain. The numbers you get back out are only the range. So technically, the definition of a function, for every element in the domain, elements are in sets, so you could think of a set of it, whatever you want, I get back how many numbers do I get back for each one I put in?
The same amount.
No, I can put in any number. How many answers come back out for a function?
Oh, 1.
One. Unique. I get a unique value in the range, or I get one and only one. That's the way math books you would say. For every element in the domain, there is one and only one element in the range. That's all it means. That's the way scientists get really anal and start making stuff up, and they don't think about what is it like to be a student who's never seen it before. They talk in language that's way higher, and teachers don't know how to explain that. Does that make sense? The numbers in is the domain, the numbers out is the range. Now you know. Okay, here's a function. Let me give you one more. X squared. If I plug in 5, what do I get back out?
25.
25. Okay. Do you agree I can put in any number into this? Here's a problem. This is not a function. So let's say X is 25. What do I get back out?
5.
Is it 5? Do I always get back 5?
Oh, it's plus or minus. Yeah.
It's plus
Or minus? That means the square root of 25 is 5, but it could be, because negative 5 squared is 25.
double
So
negative.
do you see that I'm not getting one number back? I'm getting 2 numbers back. That makes it not a function. Now, for this non-function, I still have a domain. What is the domain for the square root of X?
That'd just be the X.
What can I put into it? What numbers? Are there any numbers I can't put into it?
Negative numbers.
I can't plug in negative numbers. So the domain is all non-negative, like 0 and higher. Because if I plug in -4, it doesn't work. Take your calculator, go square root of -4, error. Not allowed. The range can be anything. Okay, so that's what a function is. So what if I said the sine of X? What numbers can I plug into this? So take out a calculator and just start plugging in any number that you want into the sine. Take 4 or 5. Just take a look at them and notice something about the values that you get back out. Can you think of any number? Is there any number you can come up with? Did anybody get, you can't do that? Any errors? What are you noticing about the numbers you get back out?
Always between -1 and 1.
Numbers you get back are between -1 and 1. So do me a favor, plug in 90. What do you get back?
You said 90?
Yes.
I got 0.89, so.
Okay. So you know what you're in? You're in radians.
Oh, okay, I didn't switch out of that.
Function. See, you can plug in degrees. That's fine. Degrees, you can do that. Even though it's a unit, it goes away when you take the sign. So make sure, plug in 90 and try it again.
1.
You get back 1.
Mm-hmm.
What happens if you plug in negative 90?
-1.
Right? So something that you could do, and you could write this out, you could say the sine of 90 degrees is equal to 1. The sine of negative 90 degrees is equal to -1. What's the sine of 0?
0.
What's the sine of 180?
0 as well.
Okay, so you're getting those numbers back. So what I would do, if I really wanted to know this, and most of you have these kind of things on your calculator, is I can plot out this function. And here I'm going to say this is the sine of x, and this is x. And I can plug in any number. But when I look at the sine, what I get is this. I get a wave. We call this a sine wave. You ever heard of that before, sine waves? Sine waves can make sounds. Just for the heck of it, hold on. Sine wave sound. Let's see if this works. Here.
Don't forget to subscribe and click on the screen of the oscilloscope. Firstly, the tops and bottoms of the square waves, human hearing, which once again aren't of any. Okay.
That's the wave. That's showing you what the wave looks like. That's a sine wave.
As you can hear, the square wave has a very much brighter and harsher tone compared to the sine wave, which is very smooth. The levels have been set to the same RMS values. So that,
by the way, just so you know, this is kind of a fun thing, and to me, it's really awesome. This is his voice. Where is it? Where is it? There? This is his voice. Let's see if I can. A sine wave is this nice pure tone. And if you change the wavelength, you're changing the frequency. And if you change the frequency, it gets you the pitch. That's really cool. And it's a nice smooth tone. But a person's voice is actually the combination of a bunch of sine waves. So here's one that says the 1 kilohertz sine wave tone. Kilohertz, 1,000 hertz, 1,000 per second. Right? That's what it is. And that represents a pitch. Anyway, that's just something I thought I would show you because it's kind of fun. Okay. That's what this plots out. Now, but in the Coriolis formula, in the Coriolis force, what is the formula? It's 2 omega v sine phi. Everybody say 2 omega v sine phi.
2 omega.
2 omega
Sine
v
pi.
sine.
Okay. What is the domain for this? What's the domain for that? Do you know what I'm asking you? Sam, do you understand what I'm asking you? What numbers, okay, what does phi stand for?
Latitude?
What numbers are latitude? What's all the numbers that I have for latitude?
0 to 90.
That's the northern hemisphere. What do you think the southern hemisphere is?
0 to negative.
0 to negative.
90.
So first of all, this is 90 degrees. This is negative 90. This is 0 degrees. So what I'm really looking at is this wave like this. Do you agree that this wave is the same going south as it is going to the north? It's just going in the opposite direction. Right? So this wave goes like this. This wave is symmetric above 0. That's why the Coriolis force deflects moving objects to the right, but in the southern hemisphere it goes the other way. It's to the left because the values are negative. So even though the wave goes back and forth, the only ones I care about, and at 90 degrees, the value of the sine function is 1. Here it's negative 1. All right, so do sine of 42 degrees, just for the sake of it, the heck of it. 42 degrees is our latitude.
.669.
Is that what you got, everybody? Okay, so that's the value. Now, what's the value of the Coriolis force at the equator?
Be 0, correct?
It'd be 0, wouldn't it? Because the sine of 0 is how much? 0. And how 0 times anything is 0. So the Coriolis force at the equator is 0, which means there is no Coriolis force at the equator. The other day we talked about geostrophic wind. What is the geostrophic balance between what two forces?
Pressure gradients and Coriolis force.
So is it possible to have a geostrophic wind at the equator? And the answer is no, because there is no Coriolis force. Coriolis force can't balance anything. What's the Coriolis force equal to at the North Pole?
Would it be 1?
Do you think it's 1? You all agree with that? And the answer is no. This is 1. But the Coriolis force is 2 omega v. Right? Because this number became 1, but I still have these things in here. All right. Do you have any questions on this before we move on past this? I want to ask you really, it's an easy question once you figure it out. Any questions on this stuff that's here? Do you understand what I'm talking about with the sine function, Coriolis force 2 omega v sine phi? V is how fast like the air is moving. All right, let's do this. Imagine that I have a globe and here is the equator, okay? And near the equator, it's not at the equator, I have a set of isobars. And near the North Pole, I have a set of isobars. This is P plus delta P. This is P plus delta P. So I'm just looking at 2 scenarios. One is near the pole, and 2 is near equator. It's not at the equator because that would be 0, right? I'm going to assume same pressure gradient force at both. The spacing of the isobars is the same in both. And the air is geostrophic. Now, I gave you a list of what, 7 facts about the geostrophic wind? Was it 7 or 8? 7. The equation is this, right? That's the geostrophic wind. I'm looking at this map. Do you agree that this is a change in pressure over a distance? If you want to think of it as being 2, right? Do you agree that the difference in pressure between these isobars is delta P? The distance between them is delta X. I said they're the same, so delta X is the same. Which wind is faster? Which geostrophic wind is faster, at 1 or at 2? You are now going to have to speak to me and tell me what you think.
Would the stronger winds be near the equator? Because since it's a sine wave, that means like the closer you are at the equator, that means let's assume it's at least below 5. So the sine wave isn't as strong, which would then in turn when you multiply it with the Coriolis force of whatever the whatever the 2 omega times v is, it would make that number much less, not restricting the pressure gradient as much.
Were you able to understand what Zach was trying to say?
It was a little rough.
Right now, Zach, if I were evaluating your rightness or wrongness, I could not give you any points because I'm not sure what you're saying. But that doesn't mean that I think you don't know what you're trying to say. You're just not communicating it yet. Ryan, what do you think?
Yeah, I'm a little confused. So the only difference between these two would be the Coriolis force, or right?
Everybody do me a favor, say Corey
Corey.
Olis.
Coriolis force.
Coriolis. That's 2 words. Coriolis. Coriolis. And people have a hard time with that word. That's fine. Yes, that is the only thing. Well, here, what's different between this at point 1 and this at point 2? I'm asking you which wind is fastest. So do you agree that it might be velocity different? Is omega different?
No.
No. Is dpdx different? Is the density different? I'm assuming, I'm not really saying anything about the density, so assume the density is the same. Okay, because you're not thinking mathematically, let's take a look at what I do when I see something like this. I solve for V. What does V equal? All over what? Oops. Do you understand how I've gone from the blue to the yellow?
Mhm.
So what I'm really saying is that the velocity is the pressure gradient force all over 2 omega sine phi. But what is 2 omega? Do you agree it's constant? What's PGF for both of these? The same. Isn't that constant? So really, what I have, if you want to see it, is I have the velocity is equal to a constant divided by sine of phi. For these two. Are you following me?
Yeah.
You're looking at me, you concentrate. So are you getting it? You following? Everybody good? Okay. So this is A equals B over C. So the latitude is smaller by the equator. Do you agree with that? Which means the sign near the equator is closer to 0. The sign near the pole is closer to 1. So who has a bigger sign? Number 1. But the bigger the sign, the velocity gets smaller. So who has a faster velocity? Do you agree? Now, Zach, you said the answer, right? Is that what you were thinking? I mean, was that part of your thought process?
Yeah, I just had to turn it and make it so the equation was solving for V. I think that was my problem.
So do you understand that I solved for V?
Mhm.
So the Coriolis force can tell you how fast will the winds be based upon what? What's really telling me how fast the winds are going to be? Well, to some extent, phi, the latitude. But what's the most important thing?
Pressure gradient.
The pressure gradient force. So the greater the pressure gradient force, the faster the winds. Do you agree this would be directly proportional? So that's what I need you to write down for another fact about the geostrophic wind. So this is number 8. The speed of the winds is directly proportional to the pressure gradient. Speed of the winds is directly proportional to the pressure gradient. But what's the difference in pressure from there to there? These are isobars. That's value P. This is P plus delta P. What's the difference in the pressure?
Delta P.
What's delta X? What's delta X?
Distance between the isobars.
Okay, so delta X is, and write this down, is the distance between the isobars. What do you call the distance between things? Like like you're gonna adjust the distance between chairs in the room. What are you changing? We do social distancing. We're supposed to be 6 feet apart, which is nonsense, but whatever. It's supposed to be 6 feet apart.
The spacing?
It's the spacing. So do you agree that the distance between isobars is called the spacing? Of the isobars. So what's the relationship between the speed of the geostrophic wind and the spacing of the isobars? Sam?
Hmm. Can you
Just-
repeat that?
Just give me words about the spacing of the isobars and the speed of the winds, because I know you know this.
Oh, I know, but I know.
What is it? Tell me.
The tighter they are, the stronger the winds.
Okay, do you agree that when the isobars are close together, the spacing is smaller? Smaller the spacing, the faster the winds. So when the spacing is small, the velocity is high. So that means what's the relationship between those two?
Inversely proportional.
They're inverse. So the speed of the winds is inversely proportional to the spacing of the isobars. When isobars are close together, we say the isobars are what? Oops. Oops. That's gracious. What do we say that? What do we say? What's the word for when they're close together, Sam? Or Lena, maybe?
I actually don't know that. I want to say tight, but I know that's not.
There we go. They're packed. Isobars are packed. I mean, isn't that what you say? Like if I said you're on a subway car and it's really crowded, isn't everybody packed in? You're tightly packed. Isobars close together, tightly packed isobars. So rule number 8 is the speed of the geostrophic wind is directly proportional to the pressure gradient, or you could say the speed of the winds is inversely proportional to the spacing of the isobars. Do you have all 9 things written down now about the geostrophic wind? Lena, go ahead and read them to me, would you?
Yes. So the pressure gradient force equals the Coriolis force.
Okay,
It moves inertially.
correct.
It's a straight line, constant speed, parallel to isobars. It flows by the Bayes ballot law,
It follows,
it-
right? It follows the law.
follows it. And then it's only true in the upper atmosphere because there's no friction. And then the last one was the speed of the winds are directly proportional to the pressure gradient.
And the last one?
What was it? The smaller spacing of isobars is inversely proportional. Oh wait, how did I say this?
Just the spacing of the isobars is inversely proportional to the speed of the winds. Or you'd probably say the speed of the winds is inversely proportional to the isobars, but really either one's fine.
Okay.
Okay? So watch this. I'm going to go to actually a model, okay? And I'm going to go to Midwest. So look at right now the spacing of the isobars. Any questions before I erase this? Okay, so over here, you see that the isobars are fairly far apart. This isobar, hold on, I need to, is 1,010, and this is 1,012. Okay, so I'll write that there for you. 1,010 millibars. That's 1,012 millibars. So what's the pressure difference across those two isobars? 2 millibars. But the distance is this far. That's the distance. And that might be, I don't know what, 120 miles? And what are the wind speeds? That's about 5 knots. Do you agree? That's how you read the wind speeds? Let me go forward in time. Now, the isobars are still 2 millibars apart, but now it's over a much shorter distance. So instead of 120 miles, it might be 40 miles. And that means the winds are not 5, but now they're 15 knots. Do you see the faster wind speeds when the isobars are close together? And if I go back to maybe the US, whenever I see them close together, I know the winds are going to be strong. Look at how close they are together out here. Look how fast the winds are. So anytime I see these things, I know that I'm going to get some strong winds. Next week, I've got some strong winds. Luckily, they're coming to us from the south. It's going to be warm. There's another storm system coming our way. We're going to be warm for a while. We don't get
That
really
one's going to be the one to watch for us.
Yeah, that would be nice if we get any moisture. I'm not sure if we are going to get moisture. Well, not bad.
Not bad.
Not a lot of Cape there, though. Of course, that's 9Z. Maybe. We'll see. All right, so that's how that works. Now, that's how the Coriolis force works. That's how the geostrophic wind works. But I need, oh God, what am I going to talk about today? I think I'll do this. Centrifugal force. Remember, which way does the centrifugal force point?
Towards the center of the circle.
Toward? Pedal means toward the center. Centrifugal is outward. So this is in, this is out. Okay? So the centrifugal force formula is V squared over R. V, well, first of all, do you agree that this is A equals B over C? R, what's R? In order to get the centrifugal force, what do you need to do? In order to have a centrifugal force, what do you need to do? This is an easy question.
I think the wind needs to be going like curved.
Right, you need to turn, you need a curve, right? So this is the radius of curvature. There's a dot on there. Curvature. Really, if Sam, if you're going on in the future, you'll need to know this is RT, the rate trajectory radius. The rest of you don't need to know that. So.
All right.
Okay. But you have to be turning. So case one, what did we say case one was for geostrophic? What did we call case one the other day? I know we kind of rushed through the end of it, so I want to kind of think about it again.
It was linear upper level flow.
So if something is going in a line, are you curving? No. So if you're not curving, do you have a centrifugal force?
Mhm.
So we're going to put this in curved upper level flow. Then you get this, but I want to talk about what the centrifugal force is. Now, first of all, Zach, what do we know about the centrifugal force? What is a fact about the centrifugal force?
It's always accelerating.
Well, the forces don't accelerate, things accelerate. What do we know about the centrifugal force?
It's a force that acts on a body moving in a circular path and is directed towards the center.
Yes. Well, the centripetal is toward the center. The centrifugal is what you would, right? You're spinning on that English rotor and the floor drops out. It feels like somebody's pushing you out. Is there anything pushing you out? It just feels that way. So what do we say the centrifugal force is?
It's an apparent force.
It's an apparent force. So I want to explain that. So what we're going to do is you're going to be driving in a car. Okay, here's your car. And you're on a date. So here you are. You're over here. And your date is over here. And you like your date. You want to get close to your date. So what do? You say nice things. No, what you do is you turn to the right. So here you are in your
I'm
car.
writing this down.
You're moving this way. That's your velocity. And so is your date. Because you're in the car together, right? You're driving down the road. But you turn to the right. So what your car does a little bit later is this. Well, I guess I'm going to do it this way. Your car, oh, hold on. You have a white car. That's a nice car. Your car does this later on. It turns. You are turning the car because you have a steering wheel that forces it to turn. Which way are you traveling? In a straight line at a constant speed. You're inertial. So relative to your car, where you keep going in a straight line, so where do you end up going? You end up going into the left wall, which stops you, and now it's going to force you to turn. So you get over here, and you go to the wall, and you're now over there. Your date keeps going straight, so as you start turning, your date comes flying towards you. It doesn't stop until your date hits you, right? And you're next to each other. I'm assuming you don't have seatbelts on. But that's what's going on. That's what the centrifugal force is. You keep going straight, but then you hit a wall, and then it pushes you to change. Your date, who's going to hit the wall first on a right turn? You will. Your date will not. Okay? So that's how you get close together. Now, if you really like your date, what are the two things you could do to get your date closer to you? What makes the centrifugal force larger? A equals B over C. You go faster, or you make a smaller curve. You turn tighter. You know, you're driving really fast, you turn too tight, you go flying, right? I mean, if whether you're in your car or not, you're not making that turn. Now, what if you don't like your date? What do you do?
Go really slow or take a wide turn.
Well, no, if you don't like your date, what do?
Get out of the car.
You turn left,
Oh.
right? Because then your date's going away from you. If you hold on to the seatbelt, your date's going away from you. If you really don't like your date, you go fast and turn left hard. If you really don't like your date, you turn left really hard and you open the door. Which I don't recommend doing, but it's funny anyway. But that's what the centrifugal force is. Now, I didn't practice this with dates, but when I was a kid, we had station wagons. Kevin, do you ever have a station wagon as a kid?
No, but I rode in a few.
Okay. In the back of the station wagon was this metal deck. And we put it down with no seats, and you just slide on it's really easy. You slide on the deck, and it's like, Dad, turn right. We go flying, and of course we elbow our siblings or whatever. But it was fun. We would fly back and forth. So think about your car going in it. Let's think about your car now experiencing you're going on a curve. Do you agree that there's going to be a very strong outward force called the centrifugal force, because your car wants to go in a straight line? And as it does that, it's going to slide off the road if you're going too fast. So to make the turn, you need to slow down or make a wide turn. But if you go too tight, you know what it's like to feel. So what do they do to the road to keep you on the road when you have a turn?
They have guardrails.
Well, the guardrails keep you from crashing, but they do something.
That's not going to stop you.
You can take fast roads. You can take a curve fast. What do they do to the road when you're making a big right exit?
Oh, they like curve.
They ramp it. Because now when you ramp it, which way is the force pointing? Into the road. Your road is actually stopping you from going out. Right? So what if I were going really, really, really fast and I went to a 90-degree turn? Then I could go around in a circle completely without falling, because there's enough force to push me. Because what's keeping me from falling down? Friction. So you could actually get a motorcycle to drive around in a basket. That's why you can do loop-to-loops. If you think about it, right? If you're doing a loop-to-loop, at the top of the loop, what force here? So imagine that you're in a roller coaster and you're doing this. When your car is here and you're sitting here with your hands up like that, what force is acting on you? Gravity, right? Gravity should pull you down. Why don't you fall out? Because you're going so fast, we have an apparent force equal and opposite that. Now, what if you went on this too slow? What would happen if you went too slow? When you got here, gravity would take over and you'd fall off the road. Right? You wouldn't make the loop, you just fall out. You know what that's like. You ever played Hot Wheels with the loop-de-loops? Go too slow and the car falls out. Because gravity is going to pull you down, just like anything else. The only thing is, for this moment, if you're going fast enough, there's an outward force keeping you balanced just for that short period of time. That's the outward centrifugal force. Right? Have you ever been on that amusement that does like this? It's like a pirate boat. It just goes faster and faster until it just barely goes over the top. Well, why are you not falling out when you're at the top? And you're going really slowly. because you've got harnesses in there, right? It's a big metal arm keeping you there. But what does everybody's coins do?
Fall out.
Everything comes out of their pockets and falls down. You ever look at the bottom of those things? You see all these coins and sunglasses and things that people lose.
What? Wait, where?
Those big rides, when you're upside down, look toward the ground and you'll see all that big metal thing has all sorts of garbage in it, coins and everything, because people lose things because it slows down. So you're not going fast enough. When you go fast enough, you won't lose it. So if you're on a roller coaster, your roller coaster is not kept up there by a metal arm. You're just going fast, and the roller coaster doesn't fall off. Because that would be bad if your roller coaster fell off. A lot of people would die. And all you have to do is make sure they have enough speed. How do they get speed in a roller coaster? As you come down, you pick up speed because gravity is acting in the same direction as you're moving. And you get down here to the bottom, you're going really fast. And then when you go up to the top, you can make the loop because you're going fast enough. And they can calculate it. It's easy. I think there's some things, it's called the physics of amusement parks. But if you did that, you better believe they're going to do this centrifugal force. So now we have, right, think about this. We have the PGF, which is -1/rho dpdx. We have the Coriolis force, which is 2 omega v sine phi. We have the centrifugal force, which is equal to v squared over r. The other force that we deal with is friction. And I'm not going to give you a formula. Here's what you need to know. Which way do you think friction points?
The opposite direction of movement.
The opposite direction that you're moving, right? It's always, because what is friction always going to do?
Slow you down.
It's going to slow you down. So friction's always acting to slow you down. There you have it. Which way do you think the centrifugal force will always point?
Outwards.
It will always point out from the outwards from the radius of curvature. So if you look in the notes in class, it says rule number 1. What does it say for rule number 1?
Is it the PGF always acts from high to low?
Right? Always acts from high to low pressure, and it'll always be perpendicular to the isobars. Rule number 2.
The Coriolis force always acts perpendicular to the rate of motion in the
Always
northern
acts
hemisphere.
perpendicular to the right of motion in the northern hemisphere. Where do you think it is in southern hemisphere?
What is it? To the left of motion?
Of course, right? And I will never give you southern hemisphere, so you don't have to worry about that. What's rule number 3?
Centrifugal force always acts outward from the radius of curvature.
And rule number 4?
Friction always acts opposite the direction of motion, causing the wind to deflect across the isobars towards lower pressure.
Why is that? Let's imagine this. Let's imagine that I have a set of isobars. And over here, the pressure is higher. Which way is the geostrophic wind blowing? Isn't it blowing that way because it follows the Bayes-Ballot law? Low pressures to the left. Which way does the pressure gradient force point?
It's the low pressure.
Toward lower pressure, perpendicular to the isobars. Which way does the Coriolis force point? To the right of wind, right? Just keep in mind, folks, that this is not toward higher pressure. It's to the right of the wind. So it's perpendicular to the right of the wind. If that's the case, then the wind is going to be equal to whatever that pressure gradient is divided by 2 omega sine phi. So I can calculate how fast the winds are based on the spacing. I need to know what the values of pressure are. I need to know the density. I need to know the latitude that I'm at. I need to know, well, I already know the omega. And then I solve for velocity, right? And then what I'm saying, if this is all that's acting on the wind, then V equals VG. So really what I'm saying is that this is the geostrophic wind, because we're assuming it's geostrophic, and that this statement up here in the left corner means the actual wind speed is what I calculate. Over there. That's what I calculate. So if I knew all these things, and I don't, right? I'm not going to give you one, but if I knew these things, I could solve it for the velocity. I know how fast the winds are. But what happens if I add friction? What happens? Which way does friction work?
It's motion.
Right? So I want you to see something, guys. This is kind of important. So are you ready? Did you draw this up? Go ahead, use colors, whatever. Tell me when you're ready. Give me a symbol if you're ready to move on. Okay. You ready, Brian?
1 second.
Okay.
I'm good.
Okay. So what I'm saying is that just a second ago, these two forces were balanced. And then I added friction. Force of friction. I added friction here. What did that friction do then? Do you understand that blue plus red originally, the Coriolis force, equaled what? What was blue plus red?
White.
No. White's the wind. Keep the
Oh.
this is the velocity of the wind. Keep that in mind. This is not a force. This is the actual wind vector. Blue plus red equaled what?
0.
0?
0. So there was no net force, which means air flows inertially in a straight line. But now I add this force acting opposite. So what will friction do? What will friction do to the wind?
Slow it down.
Slow it down.
Okay, so the wind would start to slow down. But when the wind slows down, and I'm going to write this out because it's so important. What else happens?
Would there be an effect to the isobars because when they're closer, the wind's faster, so would the isobars spread apart further?
No. Because remember, the pressure, okay, super important, what Lena kind of brought up, and I want you to think about what I'm about to say. The pressure gradient is what the pressure gradient is. I gave you the pressure gradient. It is that. What's the only way to change the pressure gradient? Aaron, do you understand that question? Right, Aaron, I'm always interested in the way you think, because you're going to be like, you like to write, right? You're good at English and you come up with ideas, right? So this is a logic thing. I'm not going to use mathematics. What's the only way to change the pressure gradient?
She's typing something. Just a minute. D, C, H. Change. P. R. Pressure. Oh, she says change the pressure.
How would you do that? Lena, what do you think? Like, I'm not sure that you're actually thinking about what I need you to think. I'm not you, everybody. Zach, what are you thinking? Or Ryan? I mean,
Would you have to like change the temperature?
okay. It's very possible, but don't worry about that's not what we're talking about. What is the pressure gradient? It's Moses's fish tank. So what's the only way to change the pressure gradient? Use Moses's fish tank to tell me, how do you change the gradient?
You would have to add or remove water from either side of the tank.
That's not realistic. You're not adding anything. Moses's fish tank, Moses is from Vegas. Sam, what were you saying? Were you talking? You had your mic muted.
Wouldn't you have to change the pressure?
Look, Moses's fish tank is this. The water over here and the water over there. I couldn't change the pressure because what's air pressure or water pressure defined as?
The weight of the water above you.
So, right, how do I change the pressure of the water here?
Would you have to lower that side's water and raise the other side that equal amounts?
Well, so what would have to happen? Wouldn't the water have to start flowing? If the water flowed that direction, what would the water look like? It'd be more even, wouldn't it? But what if the water flowed this way? Wouldn't the water level go down here and go higher here? You guys know what I'm saying? So in other words, for the pressure gradient to change, remember, it's not the pressure changing, it's the difference in the pressure over some distance changing. The water needs to flow either toward or away from high pressure. If this is high pressure and this is low pressure, then won't water flowing this way make this higher and make this lower, and that'll increase the pressure gradient. But if the water flows the other way, won't that make the pressure gradient less? Do you guys understand what I'm saying? Yes or no? You need to let me know. I'm talking a lot. You're not. So does that make sense to you? Because most people, when they're learning, would say, well, wait, do you mean this? Because you're not getting it all. Do you understand? What's the air doing right here? According to this picture, is the air traveling toward high pressure or toward lower pressure?
No, it's moving parallel.
It's moving parallel to the isobars. So it's like the water is flowing in and out this way. It's not flowing toward low pressure. It's not flowing toward high pressure. It's flowing parallel to the pressure gradient. If that's the case, will the pressure be changing? No. So I said, what happens when the wind slows down? What else happens? Something happens because it's slower.
Would it change the Coriolis force?
Why?
Because the full equation for the Coriolis force is the 2 omega velocity times sine, and since we're changing that velocity and we're making it lower, the Coriolis force overall would be a smaller number.
Well spoken, my friend. Not only did you get it right, you said it well.
Could you say it again?
Yeah, so
Let's do this, Zach, together. I'll draw, you talk.
that's the overall equation for the Coriolis force, and since we have the friction working against the velocity of the wind, that means the velocity would decrease, and because the velocity decreased, that means the Coriolis force overall would decrease as well.
Right? Which means that this force becomes smaller. Does that make sense? Which means, are these two forces balanced anymore?
No.
If I look at just the north-south direction, there's a net force pointing which way?
Towards low pressure.
The net force, there'd be a net force pointing, toward low pressure. So what would the air start to do?
Start to move towards the low pressure, like curve.
It would start to move. Instead of going this way, it would start to turn and go this way a little bit slower. That's what the air would start to do. It would go toward low pressure. But what happens to the pressure gradient if the air travels toward low pressure? Do you agree that the pressure gradient would become less? Did you just yawn on me, Lena?
Yeah, I did. I was up earlier this morning.
Okay, now watch this. So this is the new wind. I don't want you to draw this. That's the new wind. Which way does the Coriolis force point?
Perpendicular to the
Perpendicular to the new wind, right? Which way does friction point?
opposite direction.
So now the blue and the new pink and the big thick red are all different. Now there's trying to be a balance, but air is traveling toward lower pressure. But because it's traveling toward lower pressure, what does the blue force become? Less and less. So this is going to slow the air down and start lowering the pressure gradients. So you have to think about what forces do to motions if you're going to truly understand this.
This might be a dumb question. So like let's say this actually happens in the atmosphere. What would we be able to like I don't know how to say that. Like what would we see from it? Like if
Okay. So what I'm saying is, remember when I did this stuff over here, Lena?
Mm-hmm.
I said, we calculated the pressure gradient, and I said, oh, I could measure it's 2 millibars over 150 miles.
Mm-hmm.
What I would get in that scenario is I would get 2 millibars over 150 miles. I'd calculate the geostrophic wind. I'd say the geostrophic wind is 5 knots. But do you understand that I'm near the ground
Mm-hmm.
where there's friction? That's the geostrophic wind. What would the actual wind be? Would it be 5? It'd probably be like 3 knots.
Okay.
So the actual wind speed is even slower because friction's slowing it down. The geostrophic wind is the wind that I predict based upon the pressure gradient force. Let me say that again. The geostrophic wind is the wind I predict based on the strength of the pressure gradient force. Because of friction, the actual wind is slower, but the geostrophic wind doesn't deal with friction. Now, in the upper atmosphere, friction's not important. So in the upper atmosphere, the actual wind speed is very similar to the geostrophic wind. So you have to think of the geostrophic wind as being what you'd expect. In the upper atmosphere, in linear motion, the wind is what I'd expect it to be. I expect this, the actual wind is this. When the air is traveling straight, this is what I expect. So I go over here to upper atmosphere, 500 millibars. And I'm going to go here. Where do I want to go? Here. I'm saying that over here, based on this pressure gradient, the winds should be about 70 knots, and they're going parallel to those isobars. So 70 knots is what I'd expect based on that pressure gradient. And guess what? That is probably going to be the case. That is probably going to be very close to the actual wind speed. But here's something interesting. Notice that over here, the isobars are about this far apart. And I'm getting like 50 knot winds. Over here, the isobars are about the same apart, but the winds are a lot slower. The actual wind is less than I would expect with the pressure gradient. It's less than geostrophic, so we say the winds are subgeostrophic or super geostrophic, means more than that. Under what circumstance does that happen? And the answer is case 2. Before I give you case 2, do you understand what I have just said to you about this? And I know this is subtle, and here's the problem, guys, right? Here's what I see to be the problem with students like you. I told you something that is absolutely vitally important that you understand. I ask you, do you understand this? Give me a symbol, yes or no. Do you understand it? You do not understand it, Zach?
Yeah, I could use like another explanation, I think, just like one more time.
Okay. Regardless of that, if you give me this sign, you get to level 1 understanding. In order to pass this class, what level do you really need to be at? Level 3, right? Where you can explain it. And so what happens is I give you all this great information and you don't know what to do with it. So it goes away and you're like, I don't understand anymore. Now, Zach is lucky, or we're lucky that Zach says, Okay, I really don't understand it. So let me rephrase, Zach, so that you understand this, because it's that important, right? Here's a bunch of isobars. And on a map that'd be labeled. I've been labeling them some arbitrary value P, right? We've used the word arbitrary, and some arbitrary value P plus delta P, what it is, right? And I go, okay, over here at point A, how fast are the winds?
This
And if I said that to you, what would you need to know? Well, you'd say, well, wait a second. The velocity of the winds, at least the geostrophic, is minus 1 over rho dp dx all over 2 omega sine phi. So what in the right side, what do I know? Oh, well, I know 2 is 2, and I know what the value of omega is. What would I need to be told? I'd need to be told that, right? I'd have to say, well, what's the density? What else would I need to be told? Well, I need to know what delta P is, right? That's 4 millibars. Is it 8 millibars? Is it 2 millibars? What's the difference in pressure? And then I would need to know how far is it from there to there? 1 inch equals 100 miles. 1 inch equals 200 miles. I need to know something. I would have to be told these things. But it's a map, it's a location. So I'd also have to look at latitude lines so that I would be told that. So let's say that I was told all these things on the right-hand side of the equation. I could solve for the winds. So let's say I solve it and I say the geostrophic wind comes out to be 20 knots. What's the actual wind speed? Well, you'd say, is this linear upper level winds? And those isobars look like they're a straight line. So you'd say yes. Is it upper level? If it's going in a straight line and it's upper level, then what's the actual wind speed? It'd be what I just calculated. But what if this were at the ground? Would 20 knots, which is what I calculated based on only 2 things, the pressure gradient force and the Coriolis force, would that be 20 knots with the actual wind that I observe? No, because friction is going to make it slower. So the actual wind speed might be, I don't know, 16 knots. The ground slows the air down by some amount. So what I'm saying is that the geostrophic wind is what I calculate using this equation, which is a balance between pressure gradient force and Coriolis. And I solve for V. The actual wind speed becomes more difficult. You'd have to know, well, how much does friction slow the wind down? You have to tell me that. I don't know what that answer is. I know it slows it down, so I'm just guessing it's 16 instead of 20. I would think in the mountains it's going to slow it down by more than if it's over snow or the oceans or something.
Okay.
That's what I mean. Geostrophic is what I calculate based on the pressure gradient. V is the actual wind speed. But now so does that help you, Zach? Does that get you to where you need to be?
Yeah, that helps a lot. Thank you.
How about the rest of you? Did that help to go through it again? Okay. Yeah. So again, I wish I had you in class. I wish we actually had more than 5 people. It's weird teaching to 5 people. But in a normal class, when life goes to normalcy again, which if some people are in charge, it'll never go to normal, but hopefully sense will take over. When we go to class, what you do, Zach, then is you have to say, when I'm speaking, you go, wait a second, I don't really understand that. Can you help? Can you say that again? Because that's what you need to do to run your own education. you have to tell the teacher what you need.
Okay.
Now, I asked you, do you understand? And for the first, this is the first time now. Now your students are going, no, I don't understand. How many times do teachers say, do you understand? And everybody just sits there and does nothing. And then they go on. Thank God, Zach, you were truthful and you said, no, I don't understand. Force me to do it again. That's what your job is to do. How's that? Does that work for you guys? Aaron, did I help you?
Yes.
I can only imagine, Aaron, that it's tough on you, right? Because you are physically not doing anything to put it into your mind. So you have to listen. You have to be, it's all in your mind and what you see. Does that help you though, Aaron? Okay,
Yes.
so you can always go back because I want to make sure you're doing good too. All right, so case 2, what was case 1? What did we say case 1 was?
Case 1 was linear upper level flow,
So what do you think this is going to be?
curved.
And when we do that, what force do you think we're bringing in?
Centrifugal.
Centrifugal force. It's still upper level, so we're going to not worry about friction. So what I do is this. I'm going to draw in some isobars, but this time I'm going to draw them as circles. And this one is going to be an area of low pressure. So I put a big L in the middle, just so you see it. And I'm going to say that this is P. What's this up here? What's this isobar?
P plus delta P.
Right? It's going to be higher pressure, P plus delta P. And now I'm going to put the wind over here, just like I've done before. And the wind should go this way. At this point, the wind is going that way. Because it's still, as far as you know, this is still flowing parallel to the isobars. And following the bias-Ballot law. With the wind at your back, low pressure is to your left. Rule number 1. What's rule number 1? What's rule number 1, guys?
The PGF always acts from high to low.
The PGF always acts from high to low pressure. Okay, so I'm going to draw the blue arrow like that. And I'm going to say, this is my PGF. It's perpendicular to the isobars. Now, what if I said this is the point that I'm dealing with? Which way would the wind blow over there? Still going to be blowing that way, right? Pressure gradient force is still pointing that way. And the Coriolis force, what's rule number 2? Which way does the Coriolis force go?
Perpendicular to the motion.
Perpendicular to the motion. And over here, we go the opposite way. Right? Do you see that these two still look geostrophic? Does that make sense to you?
Yes.
But it's not geostrophic because this is not straight line. What's rule number 3? What's rule number 3, guys?
Centrifugal force always acts outwards from the radius curvature.
So I'm going to use green for the centrifugal force. So which way will it point? At this point, it'll point outward. And I'm going to put in here centrifugal force. Because it's outward. Over here, it would be outward century. Does that make sense to you guys? So before it was just blue equals red. Now what's it going to be? Blue must be balanced by green plus red. So the formula for this case would be that the pressure gradient force is equal to the Coriolis force plus the centrifugal force. Does that make sense to you? All right, write the equation. Give me the formula. Sam, read it out loud. Fill in what this is.
I forget really easily.
Well, what did you write down?
Haven't written anything down. I was
Well, see, that's the problem. All right, you need to be, Sam, are you taking notes on all these things?
not all of them.
But how are you taking notes when I say write this down?
Oh, I keep thinking I'll remember it.
How's that working for you?
Not very well.
Well, then obviously you're wrong in your assumption.
Yeah, I know.
You understand that writing things down is important because it causes your brain to think in a different place. Writing is different than hearing. So now you have two places it's learning it. Right? That's just the point, right? When a lot of people go to church and they take notes during church, and I never took notes. Because the reality is I'm listening to somebody talk and I'm going to forget most of this stuff because that's the reality of humanity. We don't remember here. I'm bringing you guys back over here. Hold on. The notion of that is that humanity does not remember when somebody speaks. That's not how it works. Lectures are 20%. Writing it down has benefits because it forces you to learn more. But it also causes you not to listen. So in some classes, or if I were at church, the pastor who's speaking doesn't say, "Are you writing this down? I'll wait." They're not teaching a class, they're just giving a talk. But in class, you write it down, and then I go, "Did you write that down?" Like Ryan goes, "No, just wait a second." Right? That's what a class does. So that forces you to write it down. Plus, it gives you time to process that information. So I'm just saying this, if you want to know how to get better, this is what you start. You start to do that. Now, that's not a stick, but I could make it one if you'd like. Because you don't remember.
Right.
Right? I mean, that's the point. And it's not you, that's the way humanity does. So what's the formula, Ryan? Give me the formula to write this out in really cool stuff.
So PGF is going to be equal to -1 over density times
Just what Greek letter?
Rho over the change in P over the change in X.
PDX equals.
So CF or Coriolis force is equal to 2 omega times velocity times sine, and then I forgot what that symbol is called.
What's this Greek letter?
Phi.
Phi.
Phi. And then plus the centrifugal force.
Which is?
I'm not sure how to
What's the
find
point?
that.
You wrote it down. Aaron, what do you?
Oh,
Oh, it's velocity squared over radius of the curvature.
Right. That what you were thinking, Aaron? V squared over R? Okay. So guys, say this out loud. Aaron, in your head, repeat it to yourself. -1 over rho, dp dx. Say it with me. -1 over rho,
Negative 1 over rho.
dx.
dpdx
2 omega
Yes.
sine phi
2 omega
2 omega
v
v
sine phi
sine phi
plus v squared over r.
plus v squared
plus
over
v
r.
squared over.
Okay. So Sam, I was just talking to you about writing it down. That's 2 ways. Do you understand that by speaking it, that's a 3rd way? Do you see why I say this out loud? That's a 3rd place that your brain is storing information. Visual, hearing, writing, speaking. 4 places that your brain can store information. And if all you're doing is watching and listening, you're half of that. Right? And that's why it's important for you to understand, how does the brain learn? Many ways. You know how much I listen to? I listen to audiobooks all the time. And it's great. And I'm learning a ton. And I get it. And I'm thinking through it. But I don't remember it. There's a lot of times I'm like, I got to go back and get it. Because what they said something. What did they say? I need to say it out loud, or I need to write it down. And I don't see anything because it's an audiobook. Do you know how many times I want to look at a book and read it? I wish I had the book while they were reading it. That'd be better for me. I would memorize. I'd remember more. Right? Now, obviously, I go for a walk for exercise and I'm listening to a book. I can't read a book while I'm walking. That's hard to do. So I'm limited. But I know that. I know that if I had the book, I would get more out of it. And when I speak it, like I'll tell somebody, oh, I read something today. It's awesome. Let me explain it to you. And then I have to explain it. And guess what happens when I try to explain something to them?
Can't remember.
Well, I mean, even if I remember, when I explain it to them, how well do you think I explain it? When I just heard a book and I try to explain it to somebody, I'm saying all the wrong things. I'm like, well, that didn't make any sense. Did that make sense to you? And then I have to repeat it a few times till I get it. Once I do that, I'm going to always remember that concept. That's the trick of being a good student. Now look at inside that circle, that ellipse. That's what you've learned. -1 over rho dp dx equals 2 omega v sine phi plus v squared over r. That seems really hard, doesn't it? You show your parents, this is what you're learning in class, they'd be like, what the hell, I couldn't do it. And they would say this, right? Well, I couldn't do that. But guess what? You can. Except maybe Aaron, your father, probably saying, I can do that because he's there too, right? You
you
guys
can
are,
do it better than me.
but that's what's going on here, right? I think, Kevin, that's only probably because you're worried about what Aaron's thinking rather than what you're thinking, right? But there it is, right? That's what's going on. That's the equation governing this. But here's the thing. Because I added this extra force, what happens? So what I want to do is I want to imagine this. I got 2 kids. They're playing on a teeter-totter. So what do I call this teeter-totter?
Balanced,
What'd you call it?
like balanced between the two.
There's PGF and CF. It's the geostrophic balance, right? It's a balance, just like a teeter-totter is. And that balance is really important. And then one day, now they starts going in a curved motion. And what does centrifugal force do? Centrifugal force jumps on with this side. What would that do to the balance?
Make the right side heavier.
Okay. Do you think this, like, given nothing else, this side would get heavier? What would that do to the balance?
Throw the balance off.
Right? But if the balance was off, which way would the air start to go? Toward higher pressure. That would make the pressure gradient force stronger until it was balanced. But there's something else that you can think about. Pressure gradient force was equal to the Coriolis force, and then Sentry jumped on. What's another way to make the balance work?
Decrease the centrifugal force.
Think about what you said.
Would you have to slow the winds down?
Well, now you're thinking you're a step ahead. Wouldn't the Coriolis force have to get smaller? Right? If centrifugal force jumps on there, the Coriolis force is too strong to maintain a balance. So the Coriolis force has to be smaller. Starts throwing up Twinkies, let's say. Do you understand what I'm saying here, guys?
Mhm.
Ryan, you good with that? Sam? So the pressure gradient force is balanced by the Coriolis in the geostrophic balance. Centrifugal force jumps on there. So the way that I would do it in class is I want you to think about this for a second. Here, I have two arms pulling as a tug of war on this flashlight. This is my pressure gradient. This is the Coriolis force. Okay, and in class, I would have you pulling. Somebody would be the Coriolis, somebody would be the centrifugal force. Boom, pulling in opposite directions. Does that make sense to you? But now somebody joins this hand and pulls with me. But the left hand is pulling as hard as it can. So what does the Coriolis force do? It pulls less. So this is where you were thinking really well, Zach. So how do you make the Coriolis force get less? The wind speed goes down. Listen to me, what was the wind speed? It was geostrophic. But what's the wind speed now? Slower. The actual wind speed would be slower than I'd expect given the pressure gradient. We call that sub-geostrophic. What would the air actually do in this scenario? The air would still be going in a circle parallel to the isobars. And the air would go around this area of low pressure. Which way is the air going?
Counterclockwise.
Oops. What's a better word for that? Because this is Northern Hemisphere.
Cyclonic.
And an area of low pressure is called a cyclone. So when the air is cyclonic, the wind is sub-geostrophic. In other words, I go over here and I go, hey, there's the pressure gradient. Based on that pressure gradient, I think the winds are going to be 30 knots. Because it's curving cyclonically, the actual wind speed is 25 knots. So the actual wind speed is less than what I would expect it to be given the pressure gradient force. What did I just say?
The actual wind speeds would have to be less than the geostrophic winds since it's a cyclone. Since
Well,
it's cyclonic movement.
It's curving cyclonically, right? It's turning cyclonically.
When the wind is cyclonic, it's subgeostrophic.
When the wind is cyclonic, the air is subgeostrophic. Does that mean the winds are slow?
No.
If the winds, they can be really strong, but they're not as strong as they would be if they weren't curving. Because here, let's think about this. I want to make the winds really strong. What do? If I make the pressure gradient force big, doesn't it make these two forces bigger also? But they're both velocity dependent. They're both velocity dependent. So if the pressure gradient force gets bigger, the winds get faster. But the winds will never be as fast as they would be if they were going in a straight line because of this force. So even though they're fast, they're slower than they would be if they were going straight, because they're always subgeostrophic. But I can think, what do you call an air, a cyclone that's really, really windy in the tropics? Well, isn't that a tropical cyclone? What do we call it? What's the common name for a strong tropical cyclone?
Hurricane.
That's a hurricane. Do you agree the winds are very strong in a hurricane? And the reason we can do that is because the pressure gradient force is on one side of the teeter-totter, and these two guys are on the other side. So as this side gets fatter, these two guys can get fatter. If PGF eats Twinkies, if this eats 10 Twinkies, then between the two of them, they need to eat 10 Twinkies, and we maintain the balance. But what happens in this scenario? Let me just get rid of all this stuff. Let's go back to this. Let's go back to my yellow circles. What if this were high pressure?
Wait. So does that mean that CF and Sentry are always velocity
Because
dependent?
yes, because what do you see that V exists in both terms, in both equations. Pressure gradient doesn't have V in it, does it? Coriolis is V. It depends on the velocity. The centrifugal force is V squared, V. It depends on the velocity. So in this scenario, what would this isobar be? Oh, this is P. What's this isobar?
P minus delta P.
right? It's got to be P minus delta P because it's lower pressure as you move away from this area of high pressure. So the wind is going to blow which way? Which way will the wind blow in this one?
Aaron says clockwise.
It'll go clockwise, which means at this point it's going to be down here, right? So there's the velocity, and it's going to go around, and we're going to assume it's going to be just like the other one, parallel. And it's going around clockwise, but what's a better word for clockwise?
Anticyclonic.
Anticyclonic, right? It's going to be anticyclonic. Now, rule number one. What's rule number one, guys?
The PGF always acts from high to low.
Okay, so in other words, it's going to go this way, isn't it? Outward this time? Rule number two, Coriolis force always acts.
Perpendicular to the right of motion.
So there's perpendicular to the right. It's going in this time. They're still opposite. Which way does the centrifugal force act?
Outwards from the radius.
Outward. So do you agree it's going to be this way? Now what does the balance of forces look like? Isn't it CF equals PGF plus centrifugal? What did the centrifugal force do? Do you agree that the centrifugal force switched sides?
Yeah.
Okay, read me the formula, everybody. Say it out loud.
Be -1 over
No.
rho.
Coriolis force.
2 omega time v sine phi is equal to -1 over rho dpt dx plus v squared over r.
Right? So if this is the case over here, watch. If I put the centrifugal force on this, it was balanced between these two, but now centrifugal force is going over here. What has to happen to maintain the balance?
The gradient would have to decrease, or the
Well, okay. So if this guy jumped over here, you have one of two possibilities. Either the pressure gradient force goes up. But remember, I said the pressure gradient force is the pressure gradient force. It just is. What's the other way it could balance?
the Coriolis force would have to increase.
Coriolis force has to increase. Oops. How does the Coriolis force increase?
By an increase in wind speed.
By increasing the wind speed. So if I make, watch this, you ready? If I make this bigger, then this side has to get bigger. And what gets bigger over here? You see a problem?
Yeah.
What?
The centrifugal force would also increase then.
All right, so if the winds get faster, then this guy gets faster also. But who gets bigger faster?
This.
The Coriolis or the centrifugal force? Who gets bigger faster?
Centrifugal,
Why?
because it's velocity squared, so
It's growing,
is the square. It's growing exponentially.
Exponentially.
growing exponentially. And the left side's growing
Linearly.
linearly. And at some point, I can't balance it. Now, I can for a while. I can make it work just for a while, but I can't always. Which means I don't ever get an anti-hurricane. Because I have to balance this equation over here, I can't always do it. Because if I want to make the pressure gradient force really strong, then this guy gets really big. To balance it, this guy gets big, but this guy gets too big, and the air doesn't make it. The air will blow toward away from the high pressure, which means the air, instead of curving, will start to go out. And if it's traveling toward lower pressure, it weakens or it slackens the pressure gradient. So what I'm saying is there's a limit. This is a limited idea because the velocity grows exponentially. Now, Ryan, I want you to think about something. Because remember the other day I asked you, how do you feel? And you're like, well, I gave myself a 3 on the SMART scale or whatever, right? Do you realize what you just did is you looked at this going, well, that one would grow faster because it's growing exponentially. Do you feel like is this the kind of material you thought at the beginning of the semester you could understand?
No, it
Do you
takes
understand?
a lot of work.
Well, but look at what you can do.
Yeah.
That's true about all of you. Look at what we have on the screen. Look at the level of mathematics and diagrams. And yet, does it make sense to you? Can you look at these diagrams and know what I'm talking about? That's learning. It's amazing how much your brain can understand if you learn how to learn. So don't ever cut yourself down, Ryan. Don't ever think you're less than. Because you got some serious stuff. Zach, you've been doing great today. Right, Sam? You've been doing good. Right? You're asking good questions. Aaron, how's it going with you?
You getting it?
Scale of 1 to 5. Give me your number, Aaron.
4?
4? Good. How's your dad doing it? Really, a 2? You're better than your dad.
About a 0.
Okay, so don't ever cut yourself down. Does that make sense? I'm going to show you one thing, and I want to go through this on Thursday because we're running kind of out of time. But I want to look at something here, guys. I'm just going to clean this up just for a second. Nice. Don't you like this Epic pen? What do other teachers use? Do they draw on boards for you or what? Or they just use PowerPoints?
They just use PowerPoints, yeah.
Do you like using the blackboard?
Yeah, this is really helpful because like seeing it like written out helps me a lot with math.
And you can see it as it evolves. It's not just here's the equation. You get little bits at a time, I think.
Mm.
I think that's so cool about it. So this is mathematical. Does anybody want to tell me what kind of an equation this is?
Is it a function?
No, it's a special type of an equation. And it's in my experience that the one thing that your background in mathematics has done well, it's this. Like in the years I've taught, when I ask students about things in math, I don't necessarily get good responses, but I seem to get decent responses to this type of equation.
So like y equals mx plus b.
Not y equals mx plus b, not in this one. If I look, what's the variable that I'm always solving for over here?
V.
V. Do you see V in this equation? No.
No.
And remember, I give you the pressure gradient is the pressure gradient. Remember I said this? I said, pay attention. The pressure gradient is the pressure gradient. It's just a constant. You see V in this equation? But it's only to the first power. It's linear. Do I see it in this part? But I see it here. So what kind of an equation is this?
Quadratic?
Isn't that a quadratic equation? Or what we might call a binomial? Which is ax squared plus bx plus c equals 0. Which term is the squared term? Centrifugal. What's this? What's the linear term? Minus the pressure, or because if I made it equal to 0, I'd have to bring it over here. But we're going to get messed up with the minus signs. But do you agree that's really what this is? This is binomial. This is exponential. This is linear. This is a constant. What's the solution to this equation? You remember? X equals what's the quadratic formula?
Would it be all real numbers?
No, what's the quadratic formula?
It's negative b plus or minus the square root of b squared minus 4ac over, is it c, I think? Or 2a, I think.
Right? That's what the equation is. Do you see that this is a binomial? It's the quadratic, or I don't even know what the difference between a binomial, by calling it a binomial equation or a quadratic equation. I don't know what the difference is. I think I'm going to look that up because I've never known that in 32 years of teaching. I've kind of used them interchangeably, and I'm not sure if I'm right. But does that make sense? Have you ever used, like, when you were in, hold on. When you guys were in math class and you learned this, did you ever use it? Did you ever solve an actual problem?
I remember using like quadratic formula a lot in like algebra 2, but past that, not
But
so
did
much.
you ever have an actual reason to use it? Or do they just give you equations, you solved it, and there it was?
Yeah, it just gave us equations.
You realize now you are seeing airflow is a quadratic formula. It is you use the quadratic formula to determine how fast the winds are, because that will tell you the actual wind speed. But what would you need to know? What do you need to know?
The density,
You need to know density.
the change in pressure, and the change in distance.
Right. Do you agree, guys, that this is, you'd have to know the spacing of the isobars? You'd have to know the latitude. And you also need to know what's the radius which it's curving. So you'd have to actually go, well, how big, right? Because when I look at something like this, I'd have to say, well, how far away is that? So here, watch this. Watch this. Do you agree that oh, here. Do you have any questions on this before I erase it? What I would have to do is I'd have to say this is an area of low pressure. I want to know how fast the winds are here. The air is traveling this way. I need to figure out that this is a curve. I need to know this radius. I need to know what latitude I'm at. I have to know the density. I have to do all that. But if I knew all of that, couldn't I solve this equation? So I think what I want you to do for next week is you're just going to rewrite these notes. You're going to take good notes. Sam, I want to see what you can do by going back on this lecture and taking those notes. This is like super important, don't you think, for your life? Right? You should have the intrinsic motivation. But what I'd like you to do is plugging this in. What does velocity equal? Using this formula, plug in all these terms. I want to see what that is. So you're actually, instead of saying, because this is ax squared, well, it's v squared, but what's a equal to? I'll give you a hint. What's a equal to in this equation?
Is that the radius, the r?
Except it's 1 over r, right? And then b is, you said, in other words, plug that formula in, tell me what you get. It's going to be messy. It's going to be, you got to be neat about it, but see if we can do that. And then here's a question for you. Do you understand that sometimes I can't solve this? When can I not solve this? When is there a domain issue? What limits this domain is that this value inside the circle cannot be negative. Because if it's negative, I can't take the square root of a negative number.
It would be the b value.
So the question is, and I want you to see if you can figure this out. Under what situation will this always be solvable? And under what circumstances can you not solve it? So I want you to answer this and this. And you have to use words. I'm not asking you for numbers. I'm asking you for concepts. And it's going to be challenging, guys. It's going to be hard. But listen to me. Do you agree that the last time I gave you an assignment, you didn't necessarily do it really well? I asked you to do that and you didn't. I don't want to have that situation again. I want you to work on this and try to figure this out. Now, you may not get a good answer. Maybe you're confused, but I want you to find that confusion, okay? And that's what we're going to do on Tuesday. There's no other lab. You're working on your, how many more of those chapters are you to do the worksheet on?
I'm not quite sure.
Not that many left, are there?
Yeah, maybe like 3, maybe 2.
I mean, we're getting to the end of,
Yeah, I think we have 2 more. We have chapter 9 and chapter 10.
now, I started looking at the ones that you turned in with geostrophic wind, and you had some really good notes taking on that. I was really impressed. You had nice diagrams and everything. What I'd like you to do is go back on that and say, do you understand it now? Because you were taking notes on the reading. Based on what is it, chapter, no, I don't know what chapter it was, with the geostrophic, based on the notes you did and the questions, how well did you really understand it when you read it? Give me a number of how well you understood it when you read it the first time.
First read it was like a 1 or 2. I did not understand that chapter very well.
Ryan's 2, maybe 3. Aaron, what number would you have put?
Maybe 3.
Sam, what were you at? Okay, so do you agree that when you read it on your own, your understanding is way less? I'd like you to go take a look at what you wrote down. Now that we've done a lot more, does it make more sense now? Because that's really what you should do if you want to get to a point where you're an A. You're like, okay, let me go take a look at what I did before. Oh my God, this makes so much more sense. Then I know we're going someplace. Okay, so I really want you to focus on studying, learning, getting this done. I'm not going to give you an assignment other than the fact that you need to study and to do this over the weekend. You have 5 days to get it done before Tuesday. Is that fair enough? So you don't have to turn anything in. Your grades are getting to the point where you're getting set except for the tests and the final. But I want to see how well you can learn. I want to see if you've gone someplace this semester. All right, any questions, comments? It's going to be nice, but come Monday, it's going to be in the 70s. So on Monday, maybe a little party there, right? Monday, you might have an assignment that you have to be outside for some of the day. Tuesday, you have to be here, but I'll see you on Tuesday, okay?
Okay.
All right, guys, have a good one.
Have a
Have
good
a good
one. I'll try to
weekend.
make Tuesday's class. I'll try to.
Okay, sounds good, man. See you later.
All right, see you.